We know that we can use the IGMP protocol to communicate between a receiver and an upstream router to say that that receiver wants to receive traffic for a particular multicast group, and that IGMP traffic can pass through a switch, and if it's enabled for IGMP snooping, it can know out of which of its switch ports to forward traffic. But let's now talk in this video about another multicast protocol that's used to route multicast traffic between routers, and it's called PIM, Protocol Independent Multicast. And that means that we're independent of the underlying routing protocol. We could be using EIGRP or OSPF and so on. And PIM is going to construct a distribution tree throughout which our multicast traffic is going to flow. And there are a couple of different varieties of trees. One is called a source distribution tree, and the type of PIM that uses that is called PIM dense mode. And the idea is when a multicast source starts sending traffic to a multicast group, the initial assumption is that everybody wants to receive this traffic, and it gets flooded throughout this multicast domain, going to all of our routers. Now, in this case, we see that router R3, it needs that traffic because it's got a receiver. R2 currently does not have a receiver, so it does not need to receive that traffic. But with this flooding behavior, R2 is still going to get traffic. It's going to look like this. We've got our multicast server with an IP address of 10.1.1.100, and it's sending to a multicast group of 225.1.2.3. And the source router, R1, it's going to send traffic out to both R2 and R3. When R2 and R3 get those multicast packets, they forward copies to one another. So you see, this is not very optimal right now. R3 just received 2 copies of that multicast packet, and R2 got 2 copies, and it doesn't even have a receiver attached. So after the flooding behavior, we then go into a pruning behavior. The routers will send out PIM prune messages to tell their neighboring routers that they need to be pruned off of this tree. So R3, it does not need that duplicate packet from R2. R2 doesn't need any packet from R3, nor does it need any packet from R1. So R2 sends out a couple of prune messages, and R3 prunes off that link between itself and R2, and now we're left with an optimal distribution tree. We go from the server to the source router to the last stop router out to the receiver. R2 is nowhere in the mix. And this is called a flood and prune behavior. However, there's a bit of a downside. In some implementations of multicast, this flooding and pruning behavior happens every 3 minutes. And in a very large topology with lots and lots of routers, that could be significant overhead. I know of one company specifically that deployed PIM dense mode, and this flooding and pruning behavior hurt their performance so much that they didn't even try to fix it. They just said, multicast is not for us, and they gave up on it. But now we've got this optimal tree, but let's say that another device joins off of R2. Let's say that we've got another receiver saying, I also want to get traffic destined for 225.1.2.3. Well, R2 needs to become part of this distribution tree. And just like in nature, where we can graft on one branch to another branch, you cut them diagonally and you wrap them up, we can graft on a branch to this distribution tree, and that's literally through a graft message. And R2 sends that message up to the source router, R1, saying, hey, I want to be part of this distribution tree. R1 acknowledges that. And now our distribution tree includes both R2 going to its receiver and R3 going to its receiver. And we're left with an optimal distribution tree. But there is a way around this repeated flooding and pruning behavior. We could use another type of distribution tree and another type of PIM. It's a shared distribution tree, and it's PIM sparse mode. The idea is we're going to have a router in our topology designated as a rendezvous point, or an RP. It's sort of like a meeting place. So if a router needs to receive traffic for a particular multicast group, it knows somehow, either statically configured or dynamically learned, it knows the IP address of the RP, and it's going to go to the RP and request that traffic. Here's the sequence. Let's say that we have a multicast sender that begins sending traffic. Here we have a sender of 10.1.1.100, and it's going to send traffic into its next hop router, the source router, R1. When R1 gets that new multicast stream, it knows that R2 is the RP, so it sends a PIM register message to R2 saying, hey, if you ever get anybody that wants to receive traffic for the multicast group of 225.1.2.3, you can send them to me. And R2 makes an entry in its multicast state table that if I ever have a need to get traffic for 225.1.2.3, I'll go ask R1. But until anybody does request traffic for that multicast group, R1 is not sending that traffic to R2. Nothing is being flooded across our links between the routers. But now let's say that we do have a receiver on R3 that comes up and it sends an IGMP message saying that it wants to join this group. Specifically, it's an IGMP report message, and it says, I want to belong to 225.1.2.3. And R3 also knows that R2 is the rendezvous point, so it's going to send a *G join message up to R2 saying, I'd like to receive traffic for this group. Now the star in *G is a wildcard. We're saying we do not know or we do not care who the source is, we just want to join this group. And the group is 225.1.2.3. When R2 gets that, it takes a look in its multicast state table and it says, oh, I remember, R1 registered with me earlier. R1 said they knew how to get to this group. So R2 is now going to join the distribution tree. It sends an *G join up to R1 because when R1 registered, it told R2, hey, I've got this source of 10.1.1.100, the S, that's sending traffic to the group of 225.1.2.3. That's the G in the *G join message. And now R1 is going to forward that multicast traffic over to R2, which then sends it down to R3, which then sends it out to the receiver. And the great news is the receiver is now getting this multicast traffic, and we have avoided the flooding and pruning behavior. However, there's still an issue, and that is we're dealing with a suboptimal path. Assuming all links are equal, it would be more efficient if R1 went directly down to R3 and then out to the receiver. But instead, we're going from R1 to R2 to R3 down to the receiver. But after that first multicast packet is received by R3, it can look and see who the source is. It looks at that first multicast packet and it says, oh, this is coming from a source of 10.1.1.100. And it asks the question, if I were to send traffic back to 10.1.1.100, how would I do that? It consults its IP routing table and it says, I would actually go to R1, not to R2 to get back to that address. And R3 concludes that going via R1, that's the optimal way to get back to the source. So R3 is going to send its own *G join message. It now knows the source. It learned it from that first multicast packet it received. It knows what group it wants to join. And now it's adding this branch to the distribution tree from R1 to R3. Now when the multicast source sends traffic out to R1, R1 is going to go down to R3 and out to the receiver, an optimal path. The not so good news is R1 is continuing to send traffic to R2, which then forwards traffic down to R3, which forwards traffic out to the receiver. So we end up with duplicate packets coming into R3 and potentially going out to the receiver. And when R3 sees that, it's going to send a prune message to R2 saying, thanks for initially getting me this traffic, but I no longer need it from you. And that's going to stop that duplicate traffic flowing from R2. And at this point, R2 notices that it does not have any other routers wanting traffic for 225.1.2.3, and it sends a register stop message back to R1 saying, I don't currently need this traffic, so you can stop sending it to me for the moment. And we're left with an optimal tree. Traffic goes just from the server to R1 to R3 to the receiver, and we've ended up with this optimal path without having to go through that flooding and pruning behavior of PIM dense mode.